Right, so today we're going to start drawing graphs of sine and cosine. We're going to, over the course of this topic, spend a number of lessons or a number of videos building up, adding transformations into our graph sketching of sine and cosine graphs. These can be very simple to sketch, but they can also be quite complicated. I find they're graphs that students traditionally sketch quite poorly, because they don't invest the time in planning it out properly. It's really important that you think carefully about how you're going to scale the axes, and that gets more important further down the track as we start to add in some translations as well. It's really important that you think about that first and that you scale out your axes. Now, you don't need a ruler, but if you can't vaguely accurately divide a straight line into about, 5 equal segments, then yes, use a ruler to get your scale happening, okay? It makes a big difference. If you've got a wonky scale, it's very hard to draw the sine or cosine shape. It won't be symmetric, and you'll end up with it all uneven. So it's really important that you take some time when you're drawing these. So we're going to invest some time in practicing that as well. Okay, so in the earlier video, one of the earlier videos, you will have seen how the sine and cosine shape comes from the definition of sine and cosine in the unit circle. If you need a refresher on that, please go back and watch those videos. So we're now taking for granted that we all understand what the graph of y equals sine x looks like and what the graph of y equals cos x looks like. And now we're going to start to think about applying our transformations to that: dilations, reflections, translations. Okay. Today we're going to focus really just on dilation, perhaps a little reflection. Okay, so the first thing that we understand about graphs of both sine and cosine, so here on the first page of your notes, which you can see, I can't get them both happening on screen at once here, but we have the graph of y equals sine x, which looks like this, and the graph of y equals cosine x, which looks like this. Okay, they are essentially the same shape. I want to be clear about the fact that actually this shape is called a sinusoidal wave. Regardless of whether it is a sine function or a cosine function, the shape of the curve is a sinusoidal wave. Okay, let me write that down here. Sinusoidal. Okay, that's the shape. In the same way that a quadratic function, the graph shape is a parabola. A sine function, the graph shape is a sinusoidal wave. A cosine function, the graph shape is a sinusoidal wave. Okay, we've seen previously that sine and cosine, they're actually not really different functions. They're just translations of the same function. Yeah, obviously the graph is going to be different depending on whether it's defined with a sine or a cos function, but you could equivalently come up with, if it was a cos function, you could also find a sine function that described exactly the same curve, and vice versa. Okay, so we've got our basic shapes. Y equals sine x is below. They're both periodic curves, so what that means is they repeat, okay? And we saw that in our previous definition as well. So we see that we actually only need to look from 0 to 2 pi, and we've got the complete picture of the sine curve here. So if I'm just looking at this section that I'm over drawing in blue here, if I just look at that much of the graph, and then I take that and I repeat. Same again. And I repeat. Same again. I go back this way and I repeat it. Same again. Okay, it's the same shape. The other thing I want to be really clear about, so people get sort of a bit rigid about the period, the idea of a period of a sine curve or a cosine curve, is that the period is 2 pi. So that means I could pick any point on the graph, okay, here for example, and travel a distance of 2 pi along from there, and I've got one complete period, okay. That is also, this blue section that I'm overdrawing here, is one period of the sine curve. You take that and you repeat it, repeat, etc. You have the entire sine wave. Okay, so it doesn't need to be a starting from here and finishing at here to be a period of sine. Any window that is 2 pi wide is going to give you a period of sine. Okay, so if I go from here and then look at 2 pi long from there is here. That window there is 2 pi, and so therefore that part of that graph is one complete period of sine. And you could move that window along to the left or right, and you're always looking at one complete period of sine. Take that section and repeat it, and you've got the entire sine wave. Same is true for cosine. Okay. So the period we've established is 2 pi. Okay, that's true also for the cosine function. Period is 2 pi. You look at a window that is 2 pi wide. Doesn't matter where you start and finish, you're seeing one complete picture of the cosine wave, and then you can repeat that. Okay, amplitude. So amplitude is about the oscillating behaviour of the function. So it swings from above and below. It swings above and below the x-axis in this instance, in its most basic form. So the amplitude is the distance, the maximum distance that the curve moves away from the x-axis. Okay, you cannot have negative amplitude. It's a distance. Okay, so this distance is also 1. Okay, the amplitude is 1. The graph goes from 1 above on the x-axis to 1 above the x-axis, 1 below the x-axis, 1 above the x-axis, 1 below the x-axis, etc. Okay, so amplitude of the basic sine curve is 1, and that is also true of the cosine curve. So basic period and amplitude are 1. They're really important defining features of your graph. You're not going to label those on the graph, but they're really important in enabling you to draw the graph. They're one of the first things you want to be able to identify about your equation. Okay, so then we want to have a think about what transformations are going to change those. Okay, so period is to do with x coordinates. So obviously if you were to translate the graph left or right, which is one thing we can do to change the x coordinates, you're not going to be changing your period at all. You're not creating any kind of stretch. It's stretch that's going to change the period, dilation. So dilation from the y-axis is going to affect the period. Dilation from the x-axis will be what affects the amplitude. Again, translating up and down, it's not going to change the amplitude. It'll move where the graph is, but it'll still only have an amplitude of 1. But we're going to change the amplitude by stretching the graph, multiplying the y values, and so that's dilation from the x-axis. So we're going to look at those two dilations and what they look like in equations. So we already know that when we dilate from the x-axis, this is what happens to a function. Y equals a times f of x is a dilation of f of x by a factor of a from the x-axis. So that's how we're going to change the amplitude of the function. That means that y equals a times sine of x is a dilation of y equals sine of x by a factor of a from the x-axis. That will give us an amplitude of 1 times a. The amplitude was 1. We're multiplying by a in the away from the x-axis, so multiplying the y values by a, and so the new amplitude will be 1. Okay, y equals a times cos of x is a dilation of y equals cos of x by a factor of a from the x-axis, the same thing. Amplitude of cos of x is 1. We're stretching that by a factor of a, and so our new amplitude is going to be a. Okay, I want to be a bit careful about that because we all know that the other thing that a might affect is if a is a negative number, it affects, it reflects the graph in the x-axis. Okay, so let's be really clear about the fact that amplitude is a distance, it's not going to be negative. So if, for example, we had y equals negative 2 sine x, the negative is about reflecting the sine graph in the x-axis, so it's going to go this way. Okay, the amplitude is 2. Okay, we've dilated by a factor of 2, not by a factor of negative 2. Okay, so the amplitude, the amplitude will still be 2, even if you've got a reflection. Okay, so dilations from the x-axis affect the amplitude of graphs of sine and cosine. Okay, so simple graphs, y equals 3 times cos of x. Okay, it is the graph of y equals cos of x after a dilation by a factor of 3 from the x-axis, which means the amplitude will be 3. Okay, we want to sketch the graph from 0 to 2 pi. Okay, so here we've seen we've got no period change. Okay, so the period is unchanged and therefore it is 2 pi. So we still need to think about that even though it's not changed. So the period is 2 pi. We're drawing the graph from 0 to 2 pi, so we're going to see one complete period. Okay, state the period and amplitude. We've done that in thinking about what the graph's going to look like. So 0 to 2 pi. So you're really thinking about your axes. Okay, my graph is going to oscillate from positive 3 to negative 3. Okay, so that's what my y-axis needs to do. Therefore, I need the x-axis to be right in the middle of that. Okay. I'm going to draw my graph from 0 to 2 pi. Now, something I want you to think about, which is really important in the planning, this gets more important as we add in lots of other things. When you have one standard period of the sine curve or 1 standard period of the cosine curve, I want to be clear that there are 5 key points that define this shape. And that's what you want to focus on plotting before you draw anything in, okay? So you want to work out where is your graph going to start from. That's your first key point. Then you want to use your period. Okay, my period is 2 pi, so that means 2 pi away from that starting point, I'll be at the same y value. Okay, that's my second point I want to mark in. Right, then if it's a sine curve, let's just focus on the sine one. If it's a sine curve, I know that halfway between the endpoints, I'll have another, my graph will also be at the same y value. Okay, so I'm going to mark that point. That's my third key point that defines the shape. And then I know, now you want to think a bit about reflection here, but if there hasn't been any reflection, halfway between these first 2 points I've got marked will be where I have a maximum of my sine curve, and then halfway between those next 2 points is where I'll have a minimum. Those 5 key points define your 1 period of sine. Okay, that you want to mark those in before you go in and draw anything. Same with the cosine. So work out where it starts, work out where it's going to end, 1 period. Okay. Then halfway between those 2 values is where you have the minimum value of the cosine function. Then halfway between those first 2 points is where it will be at its middle or its average value. Okay, and again halfway between the other 2 points will be at the middle again. Those 5 key points are important. Okay, you want to think about your sine curve and your cos curve as being drawn within sort of some kind of structure. You've got your middle or your average value, which with no translation will be at the x-axis, and then you've got your maximum and minimum values. And you want to be able to plot out those 5 key points. So for sine, 1, 2, 3, 4, 5. For cosine, 1, 2, 3, 4, 5. Get those right so you can get 1 period perfect. Then once you've got 1 period perfect, if your graph has more than 1 period, you then just follow the pattern and repeat. Okay, you're now looking at, you know, every this far I get my next key point. So then you just keep following on. There's one here, there's one here, there's one here, there's one here, there's one here. You just keep following your pattern and drawing in your graph. Okay, it's really important. I can't stress this enough. As I said, students I find are often really poor at drawing sine curves and cos curves, and they just don't invest the time in planning. Now this is very simple. I'm not saying this is a difficult one, but I just want us to set this groundwork here. So we've got our cos curve. We know, so it's a cosine curve, which means it will start at the top, no reflection. So at the beginning of the period, which in this case is at 0, we haven't translated left or right, we're going to be at the top, the maximum value of 3. At the end of the period, we're also going to be at 3. So that's at 2 pi. Okay. So the other thing I should have said, sorry, the point about saying that you can divide your sine or cos curve into 5 key points. So that splits, those 5 key points actually split the domain into 4 equal segments. So you want to work out where your period ends, and then you want to divide that into 4. Okay. So halfway is pi, half of that again is pi on 2, half of between here is 3 pi and 2. Okay, they're going to be the x-coordinates of my 5 key points. So starting at 0, finishing at 2 pi. Halfway between there, which is pi, is where I'll have my minimum value. Plot that point in. Halfway between those first 2 purple dots is where we're going to be in the middle on the x-axis. And halfway between those last 2 purple dots, again, will be in the middle on the x-axis. Okay, and then we can join our curve, our 5 key points up with a nice smooth curve. Okay, again, graph shape important. You're aiming for symmetry, you're aiming for smoothness. You don't want to see any cusps or sharp corners. At the ends here and here, they're points of 0 gradient. Okay, so make sure that your graph doesn't kind of launch straight up into that point. Make sure that you've got that curve happening there, that you're heading into a turning point. X-intercepts, sine graphs and cos graphs, you've often got a lot of intercepts, so unless the question really specifies coordinates, it's fine to just leave them labelled as points. I would label your minimum and your maximum values, they're key points of any function, okay, and endpoints, okay, so endpoints, also key points of any function, okay, and yeah, if you've got the space, we've only got 2 x-intercepts here, I'll label them with coordinates just to be safe. Okay, so we took a long time to draw that very simple graph, but I want to just lay out some of that groundwork to start with. Okay, second graph here, y equals half of sine x. So the number in the front is a dilation from the x-axis. So we've got dilation by half from the x-axis, which means that our amplitude is going to be half. Oops. We haven't got any dilation from the y-axis, so our period is unchanged and it will be 2 pi. Okay. Again, we want to draw the graph from 0 to 2 pi, so we're going to see one complete period. We are drawing a sine curve. So we want to think a bit about that shape. 0 to 2 pi, that's my period. I want to divide that period into 4 equal sections to help me with my, to get my 5 key points. So half of that is pi, pi on 2, 3 pi on 2. Okay. Again, our minimum and maximum value is going to be a half. So same distance either side, or else you get a skewed shape. Use a ruler if you need to. Okay. Think about your 5 key points. So it's a sine curve, so it's going to start in the centre, and at the end of the period it will finish at that same value. Sine curve, halfway between those two, it will also be on the x-axis. Now positive sign means it goes up first and then down, so halfway between these first 2 purple dots will be at a maximum value of a half. Halfway between the last 2 purple dots will be at the minimum value of negative a half. Join your 5 key points up with a nice smooth curve. With your sine curves, try not to make them too semicircular, okay? They're not like this. The shape is more like a parabola. It's not a parabola, but it's more like parabolas than semicircles, so just make sure they don't get too rounded. Okay, right, key points, intercepts, slash endpoints, maximum point, minimum point. Great. So we've drawn the graph over the required domain and we've stated the period and amplitude. Now remember also, when we've got a restricted domain, you want to be clear about endpoints. So there should be clearly included endpoints, solid circles for that particular domain. Alright, let's think about dilating from the y-axis. So we know that f of nx is a dilation by a factor of, now remember it's 1 over n from the y-axis. Okay, so that means that sine of nx is a dilation of y equals sine x by a factor of 1 on n from the y-axis. So the original period for sine is 2 pi. If we then dilate that by a factor of 1 on n, our new period is going to be 2 pi on n, and that will be the same for both sine and cosine functions. Okay, so therefore let's have a look at this first example here, or number 3. Sketch the graph of y equals sine of 4x for 0 to pi and state the period and amplitude. Okay, so the 4 in here is dilating by a factor of 1/4. Okay, so we've got dilation by factor 1/4 from the y-axis, so that is all the x values are being multiplied by a quarter, and so that means our period, instead of being 2 pi, is now going to be 1/4 of 2 pi, okay, or 2 pi on 4, which is, I'll move underneath here, 2 pi on 4, which is pi on 2. Amplitude has been unchanged here, there's no number at the front, so amplitude is still 1. Okay, so we want to draw this graph from 0 to pi, and the period is pi on 2. So we're going to see 2 complete sine curves over this domain. No translation up or down, so everything's nice and symmetric about the x-axis, so we want to keep that in the middle. Alright, we're going from 0 to pi, and that's 2 complete periods. So one period is pi on 2. Now remember, to get one period right, we want to divide that one period into 4 equal sections. I'm not going to label them all yet, we'll label the ones that are relevant, but we want to scale our axis so we've got these partitions that are going to enable us to plot out all our key points. Amplitude is 1. Okay. Alright, so again, let's get one period right and then we repeat the pattern. So it's a sine graph, which means it starts in the middle. At the end of the period at pi on 2, it will also be in the middle. Halfway between, it's also in the middle. Okay, then between those first two purple dots, we haven't got any reflection, so the sine graph goes up and then down. We have a maximum value, so up here at 1. Halfway between those 2 purple dots, we have a minimum value. And then now that we've got one period right, we can just repeat. So what we see is every, whatever this unit is, we'll work that out in a minute, every one of those we get a next dot on our graph, our next one of our key points on our graph. So we just keep following the pattern now. Along one tick on my axis, I'm now at the maximum value again. The next tick along, I'm back to the middle. The next tick along, I'm down to the minimum value. The next tick along, I'm back to the middle. I've probably got my minimum values a bit lower than my maximums. Let me just raise them slightly. And again, you might find it helpful. Another thing that can be helpful is perhaps, you know, get yourself a pencil. Let me just adjust that, sorry. You know, and rule yourself a light pencil line, you know, along at your maximum value and also down at your minimum value, all right? Just to give you structure. You want your average value, your maximum, and your minimum value, okay? Plot out your key points. Excellent. Oh, sorry, got a bit wonky there. And join them up with a nice smooth curve. Intercepts, pi 0. This is pi on 2, 0. So again, if you struggle with this is all just fraction work, okay? We've actually divided pi into 8 equal sections. So each one of those is pi on 8. Okay, and then it's just simple counting. So this first turning point is at pi on 8, 1. Next intercept is 2 pi on 8, that's pi on 4. Then we're at 3 pi on 8. Then we're at 4 pi on 8, which is pi on 2. Then we're at 5 pi on 8. Then we're at 6 pi on 8, which is 3 pi on 4. 7 pi on 8. And 8 pi on 8, which is pi. It's just counting. Take the time to scale it, and it's then just about counting. Okay, sketch the graph of cos of x on 2. Okay, so remembering that this is y equals cos of half x. Okay, so that means we've dilated by a factor of reciprocal of half, 2, from the y-axis. So that means our period has doubled. So our period is 2 pi multiplied by 2. So that is 4 pi. Our amplitude hasn't changed, so our amplitude is going to be 1. Right, we want to draw this graph from 0 to 4 pi. The period is 4 pi, so we're seeing one complete period here. Alright, no translation up or down. 0 to 4 pi, that's going to be one period, so we just want to divide that region into 4 equal sections. Half that again. Okay. Amplitude is 1. 1 and minus 1. If you want, you know, draw in a little pencil, rough pencil line just to give you some guidelines in which to draw your graph. It's a cos curve, so it's going to start at the maximum value. Okay. At the end of the period, it's also going to be back up there at the maximum value. Halfway along the period, 2 pi, we're going to be at the minimum. Between those first two dots, we're on the x-axis. Between those last two dots, we're on the x-axis. Join your curve up, join your dots up with a nice smooth curve. Four pi, 0, 3 pi, 0, 2 pi, sorry, that's not 0 up there. 4 pi, 1, 2 pi minus 1, pi 0, and 0, 1. And there's our graph. Okay, so generally speaking, if we have a times sine of nx or a times cos of nx, the period is 2 pi times 1 on n, which means it is 2 pi on n. Oops, n. Amplitude is a, although be careful, it's not going to ever be negative. So I'm going to actually write modulus of a. We no longer study the modulus in this course, but essentially it just means take a and make sure that it's positive. Okay, positive a. And the range therefore, so the minimum value would be negative a, and the maximum value would be positive a. And that is the same for our cosine curve. Okay, let's do one more to finish off this lesson. So we want to sketch the graph of half cos 3x on 2 for negative 2 pi to 2 pi. Okay, so we've got amplitude here is 1/2. We've got period is going to be 2 pi times 2/3, the reciprocal. Okay, so we can have 4 pi on 3. And then we've got our domain from negative 2 pi to 2 pi. Okay, so that's a span of 4 pi. If our period is 4 pi divided by 3, that means we're going to see 3 complete sine curves over this particular domain. Okay, sorry, 3 complete cos curves. Okay, so let's plot things out. So this time we want negative 2 pi to 2 pi, so we need our y-axis to be in the middle. We also want our x-axis to be in the middle. Okay, so 2 pi, I'm always quite bad at getting the left and right scale the same, minus 2 pi. Okay, now thinking about this period of 4 pi on 3, it will be helpful. I'm going to be able to execute that period or draw that period if I divide my axis up using thirds. Okay, so let's first of all at least, mark in pi, so halfway of each of those, that's pi. And then we're going to need thirds to help us with this particular period, so let's divide each of these regions into 3. I'm not going to label them all just yet, but each of those is worth pi over 3. Okay, great. So that scale is going to enable us to draw the graph. Our amplitude is half. Again, it doesn't really matter how big you make that, as long as it's the same either side. If you want to, grabbing your pencil and just drawing yourself in a light guideline, just to give you some structure in which to draw your graph. Okay. Now, it's a cos graph. Hasn't been translated left or right, so we start at the y-axis, okay, which means it'll start at the maximum value on the y-axis. The end of the period is 4 pi on 3, so each of our little ticks on our axis is worth 1 pi on 3, so let's just count 4 of them. 1, 2, 3, 4. Okay, so there's the end of my period there. Let's just focus on getting one period right, then it's just about repeating. Halfway along that period is where we'll have our minimum value, so that's going to be down here, corresponding with that tick there. Halfway between those two, first two purple dots is where we'll cross the x-axis, so that's going to be right there on that pi on 3. And then halfway between the last two purple dots I've got there is going to be also on the x-axis, which will be here at pi. So there we've got one period perfectly correct. Now we can just continue the pattern that we're seeing. So every pi on 3 I get to the next dot on my function. Okay, so let's continue on to the right. So at the moment we're at the maximum. The next dot will be back in the center, and that will be a pi on 3 along from here. Another pi on 3 along from here will be down at the minimum. Okay, let's go back the other way. So starting from the y-axis, back by pi on 3, we'll be back in the at the average value of the function, so on the x-axis. Back another pi on 3, we're at the minimum value of the function. Back another pi on 3, we're back to the center. Another pi on 3, we're up to the maximum value. Another pi on 3, we're back to the center. Another pi on 3, we're down to the minimum value. Okay. Now join your dots up with a nice smooth curve. If you just start drawing the curve without actually plotting out the points, you'll find that you can't keep it consistent. It'll be wider in some places and thicker in other places. It'll be taller in some places. Now again, remember these endpoints, they're turning points, so make sure your graph really curves at that point. It doesn't just head straight into that point. Right, let's mark in some points. 2 pi minus a half, minus 2 pi minus a half. And again, now it's about counting. So each of those ticks is worth pi on 3. So you can just count. So this is pi on 3, 0. This will be 2 pi on 3. This is 3 pi on 3, which is pi. This is 4 pi on 3. This is 5 pi on 3. Okay, going back the other way, so we've got 0 half up here, minus pi on 3, minus 2 pi on 3, minus pi, which was 3 pi on 3, minus 4 pi on 3, minus 5 pi on 3. Sorry, that's not 4 pi on 3, 0, that's 4 pi on 3, 1/2. And then your endpoint you've got there. Okay. So it's really, really easy. You shouldn't be solving any equations to find your x-intercepts. It's all about scaling your axis sensibly and then being able to count in fractions. Okay. All right, some practice for you to do.